Dear students, I am Dr. K. Indira from Department of Chemistry, Government PG College Jagdalpur. We are studying Auger electron spectroscopy. When a core electron is ejected either by a high energy, that is greater than 1 keV electron beam, or X-rays, an electron from a higher level will drop in to fill the vacancy. The energy released by this transition is enough to remove other electron from the same shell in the atom. It is called Auger effect, and this interaction is called Auger electron spectroscopy, AES. If a K electron is ejected in the primary process, one L electron may occupy its place in the K shell, and at the same time a second L electron is ejected from the atom, giving a doubly charged ion. It is a two-step phenomena. In the first step, an electronically excited ion A plus star is formed by exposing the analyte to a beam of electrons or X-rays. With X-rays, ionization occurs as follows. A plus H nu is equal to A plus star plus E minus. With an electron beam, excitation is A plus EI minus is equal to A plus star plus EI dash minus plus E minus A, where EI minus shows electron from the source. EI dash shows the same electron after it has interacted with A and has lost some of its energy. EA minus indicates the ejected electron from one of the inner orbit of A. The relaxation of the excited ion A plus star can occur in two ways. A plus star is equal to A 2 plus plus EA minus. This is Auger electron. A plus star is equal to A plus plus H nu F. This is the X-ray fluorescence. The energy of fluorescence radiation H nu F is independent of the excitation energy. Now, the KLL Auger process. It involves initial ejection of K electron 1s followed by relaxation of L electron 2s into the vacant K orbital 1s with the simultaneous ejection of a second L electron 2p. The kinetic energy of the ejected Auger electron E Auger matches the difference between the energy lost by the electron B as it falls into the inner shell and the energy required to remove the Auger electron C from the atom. The energy that is lost when the electron B falls to a lower shell is absorbed by the Auger electron. A portion of the absorbed energy is used to remove the Auger electron from atom, and the remainder appears as kinetic energy of the ejected electron. The energy of the Auger electron is expressed as E Auger is equal to EA minus EB of minus EC is equal to EA minus EB minus EC. This is the diagram for KLL Auger process. Now, the instrumentation of Auger spectroscopy. It consists of an ultra high vacuum chamber console, a sample carousel, manipulator unit, and a combination of electron gun or energy analyzer unit. Auxiliary equipment often includes a grazing incident electron gun and an optional ion gun for cleaning surfaces and profiling studies. Auger spectrometers are available as large beam approximate 25 μm depth profiling instruments or as Auger microprobes with beam diameter of 5 μm. The energy distribution of electrons emitted from the target NE is evaluated by scanning the negative voltage applied to the outer cylinder of the cylindrical mirror analyzer. Thus, as the voltage applied to the outer cylinder is scanned, the secondary electron distribution is measured by the current output of the analyzer. Digital filters remove high frequency noise components from the signal. Signal averaging using electron multiplier passing over a given energy range is used to ensure that the Auger peaks stand out above the noise. The choice between energy resolution and sensitivity to elements in low concentrations is to be made after the data are acquired. This is the schematic diagram of AES. It shows the electron gun, target, optional ion source, sweep supply, shields, electron detector, and data acquisition. Now, the applications of AES. Auger processes are more likely in the lighter elements except hydrogen and helium, where the core electron energy is not very different from the energies of the outer electrons. AES is therefore widely used to detect light element contaminants on metals. Any chemical bonding to a metal surface, such as by an adsorbed molecule, will necessarily change the energies of electrons in outer orbitals of the surface atoms, which means that AES gives information regarding the type of bonding which occurs. Chemical shifts can be seen by Auger spectral peaks. AES also throws light on the various oxidation states of the elements. AES is used for depth profiling analysis, wherein a change in the peak shape of differentiated spectra affects the usual peak higher estimates of concentration. Quantitative analysis by AES is restricted to elemental analysis. AES is largely used for qualitative analysis of solid surfaces, lowering agar electrons, that is 20 to 1000 eV, can penetrate few atomic layers, that is zero point 0.3 to 2.0 nm of solid. AES is also used for depth profiling of surfaces. This involves determination of elemental composition of a surface as it is being etched or sputtered by organ lines. This technique is also used to characterize the surface composition of the solid as a function of distance along a straight line of 100 mu m or less. An Auger microprobe is used to produce a beam that can be moved across a surface. Now, the scanning electron microscopy SEM. The first SEM was built in 1938 due to difficulties of chemical analysis can be done by using Auger electrons. A scanning electron microscope scans a focused electron beam over a surface to create an image. The electrons in the beam interact with sample, producing various signals that can be used to obtain information about the surface topography and composition. This is the diagram for SEM. The main SEM components include source of electron, column down which electrons travel with electromagnetic lenses, electron detector, sample chamber, computer and display to view the image. Electrons are produced at the top of the column, accelerated down, and passed through a combination of lenses and apertures to produce a focused beam of electrons which hits the surface of the sample. The sample is mounted on a stage in the chamber area, and unless the microscope is designed to operate at low vacuums, both the column and the chamber are evacuated by a combination of pumps. The level of the vacuum will depend on the design of the microscope. The position of the electron beam on the sample is controlled by scan coils situated above the objective lens. These coils allow the beam to be scanned over the surface of the sample. This beam scanning as the name of the microscope suggests, enables information about a defined area on the sample to be collected. As the result of the electron sample interaction, a number of signals are produced. These signals are then detected by appropriate detectors. Applications of SEM. It is a test process that scans a sample with an electron beam to produce a magnified image for analysis. The method is also known as SEM analysis and is used very effectively in microanalysis and failure analysis of solid inorganic materials. SEM analysis. The signals generated during SEM analysis produce a two-dimensional image and reveal information about the sample, including external morphology, chemical composition, and orientation of materials making up the sample. The EDS, Energy Dispersive X-ray Spectroscopy, component of the system is applied in conjunction with SEM analysis to determine elements in or on the surface of the sample for qualitative information. It also measures elemental composition for semi quantitative results and identifies foreign substances that are not organic and coatings on metal. The SEM is also capable of performing analysis of selected point locations on the sample. It is especially useful in qualitative or semi quantitatively determining chemical compositions, crystalline structure, and crystal orientation. Now, the references: Instrumental Methods of Chemical Analysis HCOR, Fundamentals of Molecular Spectroscopy, Benwell and E. M. McCash, Images, Source Internet, and Scanning Electron Microscopy, www.nanoscience.com, Source Internet, and www.labtesting.com, Source